All right, I'd like to jump into the Hardy-Weinberg equilibrium equation and measures of genetic variation from Chapter 2 of the text. This is a core part of where we'll be going forward in the course. All right, so we're mostly going to concern ourselves with sexually reproducing organisms, where there are male gametes and female gametes. So diploid organisms, so it takes two gametes to make a diploid zygote and offspring. And we can look at this basically as a modified Punnett square. The frequency of A1, one allele, and A2, the second allele. So we're assuming a biallelic system where there are only two alleles. Later we can consider more alleles. And they're going to have a frequency that sums to 1, basically a frequency of 1. But in a single diploid organism, if it's a heterozygote, it's 50-50. But the frequency in the population may differ from that. And there's going to be male and female gametes. They're going to come together, and they're going to give offspring of one of 3 different genotypes. Homozygous for either allele or heterozygotes. And you can get the heterozygotes in 2 different ways. Allele 1 from either the mother or father, and allele 2 from the mother or father. So we can use P and Q to represent A1 and A2, and H to represent the heterozygote, as this table from your text does. And then we can look at the different mating types and map them out. And what we ultimately get from this is P squared, 2PQ, and Q squared being the frequency of the different genotypes when we add it up and do all the math. So this is what this total below gives us. And that's ultimately the Hardy-Weinberg equilibrium equation, or it's also the binomial expansion. Now in this, I want to emphasize at this point that you need to review from Chapter 1. There's a locus, or a gene, and there are 2 alleles in a diploid organism of that gene, assuming a biallelic system. So at this point, you need to be comfortable with the difference between a locus and an allele, and why a gene, which has a somewhat more nebulous definition, is distinct. So we need to be very precise in our meanings here, because we can have a frequency of both alleles in a population and of genotypes, and they're not the same thing. Okay, so duly prompted to review again. All right, so we can look at the frequency of different genotypes as a function of a Q, the frequency of one of the alleles, as mapped here. Another thing we can do with the Hardy-Weinberg equation is, because it's the binomial expansion, P squared, 2PQ, Q squared, we know what to expect in a population that meets the assumptions of this equilibrium theory, that there's no migration, no mutation, no inbreeding, or that there is random mating, that there's an infinite population size, and that there's no selection. If we have that, that's what we expect, an expected number or an expected frequency of different genotypes based on the allele frequencies. We can then go into populations and observe what the frequencies we see are. And when they differ from one another, we can look for which factors affect that. So it makes this theory very useful for testing different factors that may cause deviation from Hardy-Weinberg equilibrium. So we can do this with all sorts of systems. We can use ones that are more complicated. It extends quite simply to systems that have more than 2 alleles. We just add P, Q, R, S, T, and so on. But the math works the same way in a diploid organism. And for many different phenotypes that are caused by a single allele, often colors in both plants and animals, like colors of different kinds of cats, we can look at expected and observed frequencies, such as the lack of orange or cats, where the system happens to be X-linked and unusual in cats. So this table, it's table 8 from your text, shows you how to modify the Hardy-Weinberg approach for haploid, organelle, and Y chromosome, as well as for cases where there's dominance, which does affect the phenotypes we observe because the heterozygote is the same as the homozygote. An interesting one are the spirit bears of British Columbia, where you get white-colored grizzly bears. In some populations, it's caused by a single gene. And though this is some data aside from this paper showing these phenotype and genotype frequencies. We have a variety of tests to show that these frequencies differ from one another. Ultimately, we use the chi-square test, or a maximum likelihood deviation from it, or a Fisher's exact test, which is basically a chi-square test, to look for deviation of observed from expected. So the test is a chi-square test. Another famous system are melanic pepper moths from the British Isles, and their increase in frequency during the peak of coal burning in England. I'd like to end there, keep it short. There'll be more coming.